Hello everybody, and this is Mikhail Porosyan from MP Home Studio with lecture number 24 from the series Monotone and Steady Probability. Okay, today we're gonna talk about some important discrete random variables. We're gonna study Poisson distribution, negative binomial distribution, hypergeometric distributions. The first part of this video, the first video will be devoted to Poisson distribution. Poisson distribution's name is Poisson for short, or PO sometimes. It has just one parameter lambda, and lambda is positive, any positive number, and lambda is called the rate per unit of measure. We will talk a lot about that parameter later. So the definition is the following. We say that the random variable x has a Poisson distribution with rate parameter with parameter lambda, and we will write in this way: if the probability mass function of x is given by this formula. So the probability that x will take the value k is e to the minus lambda times lambda to the k over k factorial for any k running from 0 to plus infinity. So the range of our random variable x, of Poisson random variable x, can be any non-negative integer number. In the table form, the PMF will look like the following. So the values of x can be any non-negative integer, 0, 1, 2, etc., k, etc., up to infinity, and the probability that x will take the value 0 is, well, I am plugging here k to be 0. I'm getting just e to the minus lambda. The probability that x will be 1 is e to the minus lambda times lambda to 1 over 1 factorial, etc. The probability that x will take the value k is e to the minus lambda times lambda to the k over k factorial, etc. And it is an easy exercise that the sum of all these probabilities will give 1 when k is running from 0 to plus infinity. Just try to solve that problem. Let's get that identity. So usage of Poisson distribution. This is one of the most important distributions in probability, and it has a lot of applications, and I will give at the end a lot of examples for you by using R, by fitting data to Poisson distribution. But first, let's talk about in which cases and how Poisson distribution is used. So Poisson distribution is modeling the number of times a rare event occurs in a fixed interval of time or fixed interval of the space, fixed area of space. And lambda, the parameter of that distribution, is the rate of that event per unit of a measure. Say per minute, the rate per minute, the rate per hour, per meter square or square centimeter, and etc. We will have a lot of examples of this form. So some notes. Lambda, the rate parameter, is the average number of events, that rare events, per unit of measure, of per unit of time or per unit of area. Say the average number of events in 1 hour per hour, or the average number of events per minute, or average number of events per meter square, etc. So lambda is the average number of events. Later, when we will talk about the expected value or the mean value of random variable, we will go back to this again. If x is a Poisson random variable, then its range is 0, 1, 2, 3, 4, etc. So it takes every non-negative integer value. And one important thing, do not read Poisson distribution as Poisson distribution. This is Poisson in French. Okay, by the way, Poisson in French means fish. Some examples of Poisson distribution. We can model the following events by using the Poisson distribution. And we will talk about some of them. Say the number of emails received per day. Or we can use Poisson distribution to model the number of phone calls in a day for a person or some call center. We can model by Poisson distribution the number of car accidents at some place between, say, 9 a.m. and 9 p.m. Or we can model by Poisson distribution the number of misprints in a page of a published book or in a newspaper, or the number of defective items in a production batch, or the number of network failures in a day. Also, we can model by Poisson distribution the number of earthquakes in a year, the number of goals in a football game, and a lot more and more examples. So I will give a lot of examples in this lecture. I love talking about Poisson distribution. I love this. I like very much this distribution, so I will give some examples how this can be applied to model real situations. Okay, so another note about when the Poisson distribution is an appropriate model. So from Wikipedia, we have the following test. We can use the Poisson distribution if the following assumptions are true. There is a fixed interval of time or space during or in which we are considering our events. Say we are considering per minute, every day, or every month, or every year, or every day from this to that, or every square centimeters, etc. So there is a fixed interval of time or space. X is the number of times an event occurs in an interval, in that interval, and X can take values from 0 to plus infinity, any non-negative integer values. The occurrence of one event does not affect the probability that the second event will occur. So the events occur independently. This is independence assumption. And finally, the rate at which events occur is constant. So the rate cannot be higher at some intervals and lower in other intervals. Of course, the number of events X will vary because it is random, but the rate needs to be more or less constant, the same. So in that case, we can model X as a Poisson random variable with this rate, with some parameter lambda. And sorry, I forgot about the last one. So two events cannot occur at exactly the same instant. Okay, in this case, we can model X as a Poisson random variable. So our first example, which of the following random variables can be modeled as a Poisson random variable? X is a number of X is a number of cars passing by my window in an hour. So X is a random variable. X is changing from hour to hour. Last hour, say 5, X was 5. For the previous hour, X was 3, etc. So can we model this X by using Poisson random variable, by using Poisson distribution? In fact, no, because the number of cars will depend on the time of the day. Say when I will consider, say 1 a.m. to 3 a.m., X will be very low. If I will consider, say 10 a.m. to 12 a.m., 11 a.m., then I will have X is not so small, say 3, 4, or 5. So the rate, hourly rate, per hour rate, is not constant here because that is changing from hour to hour. So Poisson distribution is not so appropriate for this random variable x. Okay, why is the number of cars passing by my window between 10 a.m. and 11 a.m.? This is pretty much of constant rate. Well, it depends on the day, of course, but the variation of the average number of Ys of cars passing through from 10 a.m. to 11 a.m. will be constant. That rate will be constant. So I can use Poisson distribution for this random variable y. Z is the number of calls at taxi center per hour. Again, Z is a random variable. Z can be, say, 12, Z can be 20, Z can be 100, Z can be 0, etc. So the rate per hour rate of number of calls is not constant. Well, in the night, Z will be very small, and during the day, Z will be high. The hourly rate of number of calls will be high. So it is not so wise to use Poisson distribution to model Z. But say if we are talking about the number of calls at some emergency center per hour, this can be pretty much modeled by using Poisson distribution, because the average rate per hour will be the same even at the nights. And finally, U is the daily number of absent students from our probability class. Well, again, the rate will vary from day to day, of course, but the rate will be much higher when we are doing our quizzes, and the rate will be smaller when we will do rate of absence. The number of absent students will be smaller when we are doing quizzes, and the number will be much higher. Hopefully this is not the case when we will talk about other days. So U is not so pretty much close to Poisson random variable, so we will not use Poisson random variable to model this U. So the idea was we need to have some same rate, same average number per that unit of time we are considering to be able to use that Poisson random variable. Okay, so let's move forward. Now assume we have a random variable x which has a distribution Poisson 4. So the rate parameter is 4. The problem is asking to find the PMF of x. So the PMF of x is the following. Let me write it here. So x is taking values 0, 1, 2, 3, 4, etc. So infinite number of them with probabilities. So the probability that x will take the particular value small x. If x is 0, so x is taking the value 0 with the probability e to the minus lambda, and lambda here, lambda is 4. So lambda is 4, sorry. Lambda is 4. E to the minus 4. The probability that x will take the value 1 is e to the minus 4, e to the minus lambda times lambda to the k is 1. So 4 to 1 over 1 factorial. the probability that x will take the value 2 is e to the minus 4 times 4 squared over 2 factorial. The probability that x will take the value 3 is e to the minus 4 times 4 cubed over 3 factorial, etc., etc. Okay, this is the PMF of our random variable x. So find the probability that x will take the value 2. So the probability that this is 2, the probability that x will take the value 2 is given by e to the minus lambda, that is e to the minus 4 times. We need to take this. Unfortunately, after going back and forth, something is happening with my writing, so it is not visible. So we have 4 squared over 2 factorial. And we can calculate this number, say, by using some calculator or R. So this is the probability that x will take the value 2. Let me erase, because after going back, this will not be visible. So the next is calculate the probability that x will take values between 3, including 3, and 5.5. So this is equal to, because x can take only values, so the values of x can be either 0 or 1 or 0 or 1 or, 2 or 3 or 4 or 5 or 6, etc. So only the values 3 up to 5 will satisfy this inequality. So 3 for x can be either 3 or 4 or 5 to satisfy this inequality. So this is the sum of probabilities that x will take the values 3 plus x will take the value 4 plus probability that x will take the value 5. And by using that PMF table or PMF formula, we can calculate, let me erase this, we can calculate this probability easily. So I am calculating this. So probability that x will take the value 3 is, let me write here the formula, x is taking the value k with probability e to the minus lambda, lambda is 4 here, times lambda to the k over k factorial. So here we will have e to the minus 4, because lambda is 4, times 4 cubed over 3 factorial. So I'm plugging k to be 3, plus e to the minus 4 times 4 to 4 over 4 factorial, plus e to the minus 4 times 4 to the 5 over 5 factorial. So this is the probability that x will be between 3, including 3 and 5.5. Let me calculate this number, this sum, by using R. So I'm switching to R. This is my R. Let me erase this. So the name of Poisson distribution in R is Poisson. So if I will write d Poisson will give the PMF of that Poisson random variable. So I'm writing d Poisson. Here I need to write x, at which point I'm calculating. So for which k I'm calculating the PMF, and I need to give the lambda. So say I want to have what is the probability that x will take the value 3 if my x is Poisson distributed with parameter lambda is equal to, say our lambda was 4. If I will run this, I'm hitting Control Enter, that is giving 0.19 here. So the probability that x will be 3 is 0.19. Okay, so our problem was to calculate the sum of probabilities that x is equal to 3, x is equal to 4 and 5. So if I will write something like this, so 3 to 5 is giving a vector from 3 to 5. So this will return a vector if I will run that, and I am running. So this is the probability that x is 3, this is the probability that x is 4, this is the probability that x is 5. Now I can just add them by using sum. And I'm writing another parenthesis and I'm running. This is 0.55 about. So the probability that x will be between 3 and 5.5 is 0.55. Okay, let's go back to our example. So the next is find f at 3.1, where f is the CDF of our random variable x. So by definition, the value of our CDF at 3.1 will be the probability that x is taking values less or equal than 3.1. And this is the same as to write, because x can take only non-negative integer values. This is the sum of the following probabilities. So x is equal to 0, probability that x is 0, or probability that x is 1. Because these events are disjoint, I can add that probabilities. Probability that x is taking the value 2, or the probability that x is taking the value 3. And by using that formula for calculating the PMF of our Poisson random variable, I can write the following. So e to the minus 4 times our lambda 4 to k over k factorial, and k is running from 0, so from 0 to 3, Let me just recall that 0 factorial is by definition 1. So I can calculate this sum again by using R, but I will not do that. Okay, so let's move forward. Sketch the graph of the CDF of f, CDF the CDF of that random variable x. So the CDF will look like this. Later I will do that graph by using R. This is x, this is our CDF f. So we will have something like this. This is x is a discrete random variable, and its values are 0, 1, 2. So I will have something like this. I will have 0 up to 0.0. So this is 0. This is 0. Then I will have small jump, and the jump size is the probability that x will take 0, which is the probability that x is taking the value 0 is e to the minus lambda, which is 4, so e to the minus 4. So up to the 0.1, I will have a constant function, so something like this, an arrow here. Then up to the 0.2, I will have another constant. Here I have a jump of size, the probability that x is taking the value 1. So x is taking the value 1 with the following probability. So e to the minus 4 times 4 to the 1 over 1 factorial, which is the same as 4 times e to the minus 4. So a little bit larger jump. So this jump size is 4 times e to the minus 4. Then up to the point 3, I will have another constant. And this jump size is the probability that x is taking the value 2, etc., etc. So we will have something like this, up to 4, then up to 5, then up to 6, etc. And this will converge, in fact, to 1 when x will go to plus infinity. So we will have this kind of steps converging at plus infinity to 1. Okay, so let's move forward. The next example, assume that the average number of traffic jams during a day at the Arshakuniats Avenue is approximately 2.3. Okay, assuming that for the number of traffic jams, the Poisson model is appropriate, let x be the number of traffic jams today. X is a random variable, we do not know the exact value, but we know the distribution, it is Poisson with parameter 2.3. So we assume that x is Poisson with lambda, parameter lambda, find lambda, and lambda is the average number of traffic jams during a day. So traffic jam today, so today we are talking about one day. So lambda is 2.3. The problem is asking to write down the PMF of x. So the PMF of x, let me erase this and write on the board, or maybe I will write it here. So PMF of x will be, x is taking the following values, so 0, 1, 2, etc. And the probabilities are the probability that x will take the value small x, say 0, with probability e to the minus lambda, and lambda was 2.3. So this is our lambda. Lambda is equal to 2.3 and minus 2.3. The probability that x is taking the value 1 is e to the minus 2.3 times that lambda 2.3 to 1 over 1 factorial, which is 2.3 times this e to the minus 2.3. The probability that x will take the value 2 is e to the minus 2.3 times 2.3 squared over 2 factorial, etc. So the general formula is again given by the following, in the following form. So e to the minus lambda, so e to the minus 2.3 times that lambda to k over k factorial for any k running from 0 to plus infinity, 0, 1, 2, etc. So this is the solution of that second part. Let's move forward. So the next part is to calculate the probability that no traffic jams will be today at Arshakuniats Avenue. So because x was the number of traffic jams, so no traffic jams means that x is equal to 0. So problem is asking to calculate the probability that x is equal to 0. And the probability that x is equal to 0 is this much. E to the minus lambda, e to the minus 2.3. Calculate the probability that exactly 2 traffic jams will be today. So this is again easy. Probability that exactly 2 traffic jams. So 2, this is equal to e to the minus 2.3 times 2.3 squared over 2 factorial. And we can calculate this by using our R. And the next problem is calculate the probability that the number of traffic jams there will be more than 5. So if the average number is 2.3, the probability that we will have more than 5 traffic jams is not so probable. Let's calculate that. Let's see what is the probability that we will have more than 5 traffic jams. So probability that x is the number of traffic jams is larger than 5. This is equal to, well, either I need to write the sum of probabilities for x is equal to 6, 7, 8, 9 up to plus infinity, or I can use the formula for complement and of an event and write this probability is 1 minus the probability that x is less or equal than 5. And this is equal to 1 minus the sum of probabilities that x is equal to 0, then x is equal to 1, then x is equal to 2, up to 5. So I can write that in the form of a sum. So here I'm writing the probability that x is equal to k, and k is running from 0 to 5, including 5, because 5 is included here. And here I need to write the probability that x is taking that particular value k. So e to the minus 2.3 then times 2.3 to k over k factorial. And let's calculate this probability, the probability that x will be, the number of traffic jams will be more than 5 if the average is 2.3 and x is given by Poisson distribution by using R. So I'm going to R, so I'm erasing this, I'm going to R, this is our R. And now I need to calculate the following. 1 minus, so the complement, I need to add from 0 to 5, so I'm calculating the probability, the PMF at the PMF of Poisson, here is the Poisson distribution, for 0, 1, 2, up to 5, and my lambda was 2.3. Okay, and I'm running this by hitting Alt and Enter in this case, and the probability is just 3%, 0.03. Okay. Okay. Important relation between binomial and Poisson distribution. It is important that Poisson distribution is the limiting case or approximation of binomial distribution, of binomial probabilities. Let's talk about that and solve some problem about that approximation. Recall that when doing n independent trials with probability p of success in each trial, so we have an experiment, simple experiment, an event called success. The probability of that success is p in each experiment. We are doing that experiment n times independently, so we have n trials. Then the probability of having exactly k successes, by x we are denoting the number of successes, so probability that we will have exactly k successes given by our famous binomial probabilities. Okay, and now assume that n is large, the number of trials is large, but the probability p of each success is small enough, and that's what we call rare events. So p is small enough, the probability of each success is small enough. And let's denote by lambda the product of n and p. So n times p is our lambda. Then one can prove that this binomial probability, the probability that x is equal to k, is approximately equal to e to the minus lambda times lambda to the k factorial. So we can calculate binomial probabilities. If n is large, p is small, and lambda is their product, we can calculate by using Poisson probabilities for the same k. Poisson probabilities for that same k, and lambda is n times p. So let me give the sketch of the proof that this is close to that Poisson probability. So what we are trying to prove is the following. So I'm writing binomial probabilities. So n choose k times p to k times 1 minus p to n minus k. So we are assuming that n is large, p is small, and lambda is equal to n times p. So from here I can calculate p, so p is lambda over n. So let me plug here p instead of p, lambda over n, and also write the formula for that binomial coefficient. So n factorial over k factorial times n minus k factorial times p to the k, which is lambda over n to k times 1 minus p, which is 1 minus lambda over n to n minus k. So what I'm doing here is the following. I'm grouping and cancelling some terms. So lambda to the k, I have lambda to the k here. So I'm writing it here. This is lambda to the k. I have k factorial. I'm writing that k factorial here. So I have this. I have lambda to the k. I'm cancelling n factorial and n minus k factorial. I will have the following: n times n minus 1 times n minus 2 up to, well, n minus k here and here will be cancelled, and I will have n minus k plus 1. And this divided by, well, I have cancelled this and that, so I have this term from that cancellation. I have n to the k, so I'm writing n to the k, n to the k here, and times I have here 1 minus lambda over n, 1 minus lambda over n to n times 1 minus lambda over n to minus k. Okay, let's move forward and write this product in the following form. So I'm writing the same thing here, lambda to the k over k factorial times, well, I can cancel one of the n's. So in fact, I want to divide separately each term of this product. So n over n times n minus 1 over n times n minus 2 over n, because we have k terms here and k terms here, n times n times n, k times. So I can write instead of this ratio the following. So one of the n's will be cancelled. I will have n minus 1 over n, which is 1 minus 1 over n, 1 minus 1 over n. Then n minus 2 over n, so I will have 1 minus 2 over n. Then etc. The last one will be n minus k plus 1 over n, which is 1 minus k minus 1. Please note that I'm writing minus here over n. Okay, this ratio is equal exactly to this product, and times the rest is the same. Lambda over n to n, and times 1 minus lambda over n to minus k. Okay, now let's calculate the limit when n is tending to infinity. So when n is large enough, if n is tending to infinity, because this is independent on n, this will remain the same. This is a constant now. So if n is tending to infinity, this will tend, we have just finitely many terms here. So k minus 1 terms here, and each of them is tending to, when n is tending to infinity, let me write, n is tending to infinity. So this tends to 1 when n is tending to infinity, because this tends to 0. This again tends to 1. This again tends to 1. Because we have finitely many terms, this is important. Then we will have, the product will tend to 1. Okay. What about this? If n is tending to infinity, so n is tending to infinity, this is tending to 0. So this tends to 1, but this tends to infinity. So we have indeterminate form 1 to infinity. But from calculus we know that this is tending to e to the minus lambda. This is very important and famous limit. So the limit when n tends to infinity is e to the minus lambda. Now, when n tends to infinity, so n tends to infinity, this tends to 1, and this is fixed constant, so this will tend to 1. And finally, we can calculate the limit. We have the limit of this product of this probability when n tends to infinity. So we have this lambda to the k over k factorial, and times, this is 1, this is e to the minus lambda, and the other one tends to 1. So we are getting that binomial probabilities. So if y is a random variable with Poisson distribution with parameter lambda, which is lambda is n times p, then we can write something like x is close to y. Later we will talk about this. Later we will talk about convergence or closeness of one random variable to another one if n is large and p small. Okay, this much about the proof of that approximation. Okay. Sometimes when we solve a problem with binomial probability distribution, when large number of trials and small probability of success is given, then we can approximate by using the previous formula the probability of having k success by using Poisson distribution. When x is binomial with parameters n, p, then we can approximate p. We can calculate the probabilities concerning this random variable p with Poisson random variables where n is large and p is small. And we can approximate by the following. So we can assume that this x is approximately Poisson, x is Poisson, with parameter lambda, where lambda is n times p. And we have an estimate for the error for that approximation. This is known, this is proved in advanced probability courses, that if x is binomial with parameters n, p, and y is Poisson with the parameter lambda, which is n times p, then the probability that x is this binomial is in some set minus the probability that y is in that same set. Say a probability that x is equal to 3 minus the probability that y is equal to 3 is less or equal than the minimum of p and n times p squared. Not so easy to prove, but we have this kind of beautiful estimate for the error. Okay. An example, assume that the probability of having a broken egg in the box is 0.5%. So tomorrow one of the supermarkets will receive 1,000 egg boxes. So what is the probability that exactly 6 out of that 1,000 egg boxes will contain broken eggs? So this is clearly a binomial model, binomial case. And say success is having a broken egg in egg box. The probability of success is, so we are solving the first part by A. So first let me write the probability of success. So probability of success, well, having broken eggs is not a success, but in this term, in probability course, this is a success, is 0.005. So we are doing 1,000 hopefully independent trials, and we are asked, assume that X is the number of broken eggs, in 1,000 boxes. Then we are asked to calculate what is the probability that exactly 6 out of that 1,000 will contain broken eggs. So we are asked to calculate this probability that X is equal to 6. Okay, we know that X is binomial, so binom, with parameters n, 1,000 and p. And we can easily calculate the probability that X is equal to 6 by using that binomial formula. So binomial formula says calculate n choose 6 and choose k. So 1,000 choose 6 times p to the 6, so 0.005 to 6, times 1 minus p, 1 minus 0.005 to 1,000 minus 6. 1,000, this much non-broken X in 1,000 boxes. Not non-broken X, this much boxes with non-broken X. Okay, and we can calculate this by using R. So R will give the following. Let's go to R. So go to R. So now I'm erasing this. So erase. Yeah. P is equal to 0.05, 0.005, sorry. N is equal to 1,000, number of boxes, and we are calculating the probability, so the value of our PMF for binomial distribution, where k is equal to 6, the probability of having exactly 6 successes, 6 broken X, 6 boxes with broken X, sorry. So I need to write the binom, the PMF of binom. X is 6 for 6. I'm interested in having exactly 6. So size is equal to n. So we are doing n experiments, n boxes, and the probability is p, of course, p. If I will run this, I will get 0.1465 here. I have that probability. Okay, going back to our problem, we have solved this, and now using the Poisson approximation, Let me solve first on paper, here on slide. So by using Poisson approximation, we are doing the following. N was 1000, P was 0.005. So lambda is equal to N times P, which is 1000 times 0.005, which is 5. Now, I'm assuming that approximately X is Poisson with parameter lambda, which is 5. And having this, I can calculate the probability that X is taking the exact value 6, that we have 6 boxes with the broken X. So this is equal to, by the PMF formula for Poisson distribution, e to the minus lambda, e to the minus 5 times lambda to k, lambda to, so lambda is 5 to 6 over 6 factorial, lambda to the k over k factorial. And let's calculate this probability and check if they are the binomial and Poisson ones give close values for this for that probability. So we are calculating lambda is 5, the probability that X is 6 when X is Poisson with parameter 5. So I'm erasing this, going to R. Now lambda, say L is N times P. So I'm running this. Yeah, L is 5. And now I need to calculate the probability that Poisson random variable, so D plus, because we are talking about Poisson, now approximation, X is 6. I'm interested in having 6, so the probability of 6. And lambda is equal to our L, which is 5. So I'm calculating this probability, and you can see that we have very close values here and there. In fact, let me show here by using R that kind of thing. Say, let me draw the PMF for binomial and for Poisson in this case. So for that, I have this P, I have N, and I have lambda. I want to draw first Poisson probabilities. So let me calculate probabilities. Say X is running. I need to calculate it for different values of X. Say X is equal to 0, X is equal to 1, X is equal to up to, say, some point 12. Say X, I'm running my X from 0 to 12, say. I'm calculating the values. Let me give a name to this. The values of my binomial PMF at the point X. So what I'm doing here, first I'm calculating the PMF value when X is 0, then PMF value when X is 1, then PMF value when X is 12. And I'm keeping that in the vector Y, and then I will plot the values of X, Y. So I'm running this, yeah, Control Enter. Next, I want to plot that, so plot X, Y. Okay, so let me show that plot. Yeah, we have this kind of picture. Let me do the following. Let me give parameter type is equal to age. So I will have this kind of picture. Now I want to draw for the lambda, which is equal to N times P, the Poisson PMF values. So to see that binomial and Poisson for the case when lambda is equal to N times P are very close to each other. When N is large, P is small. Okay, so I need to do the following. I'm calculating the values of Poisson PMF at the same points at 0, 1, 2 up to 12. I'm keeping this in, say, z, another variable, another vector. So this is z, and I want to add that xz over the same graph. And let me just give a color. Color is equal to, say, red. And you can see that I have pretty much close values for both binomial and Poisson probabilities. Okay. By the way, how to read this diagram? Say the probability that x will take the value 5 is this much, 0.58 maybe. The probability that x will take the value 4 is 158 maybe. And the probability that x is taking the value 4 is 0.158, etc. So the probability that x will be 10 is small enough. The probability that x will be 12 is small enough. And recall that L was the average number of events, in this case, broken boxes with broken x. And if the average number is 5, as in our case, average number is 5, the probability that we will have, say, 12 boxes with broken x is very small. The number of broken boxes will be random, but the number of broken egg boxes will be close to that average number, close to 5. And you can see that highest probabilities are when x is close to that 5. Okay, let's move back to our lecture, to our slides. We have solved this problem. Let's move forward. I want to stress that this is important, that Poisson distribution is not just an approximation of binomial distribution. People are using as approximation for binomial distribution. People are using Poisson as approximation of binomial distribution. But it is another approach of solving probability problems about calculation of number of rare events. And let me explain this by giving some examples. Let me explain why sometimes it is more appropriate to use Poisson distribution. Now, consider the following example. So assume we are considering a publisher who publishes books, and sometimes, of course, but very rarely, hopefully, we can find misprinted characters in that books. So we want to model the distribution of misprinted characters in a page for that publisher. So let x be the number of misprinted characters in a random page of a random book of that publisher. So x is a random variable. It is a number of something, misprinted characters. Misprinted characters are rare, so this is a rare event. X is calculating the number of rare events, and we want to model this random variable. So we will give two approaches, two models. First, we will use binomial, then I will use a Poisson and make comparison and see what is happening for binomial, what we need for binomial case and what we need for Poisson case. So first, the binomial model. For the binomial model, we need to have the following things. We need to have the probability of having a character misprinted. So this is, if character is misprinted, say it is our success, and we need to have the probability of success for a character. This is for one experiment, the probability of success. Say we'll assume that p is equal to 1 over 50,000. And this can be done by using statistics, of course. But we are not in the statistics course, we are in probability course. We are assuming that this is given. So p is 1 over 50,000. Among 50,000, you can think like this, among 50,000 characters, there is just one misprinted one. We need to have, for binomial model, we need to have the number of trials, so the number of characters in a page. Say we will assume that n is 3000, so we'll assume that page has 3000 characters. And we need to have independence of the trials, so independence in making misprinting characters in different positions. Say in probability of having a misprint in the third character and having the event, not probability, event of having misprint in the third character and event of having misprinted 10th character are independent. We're assuming that we have independence. So I will change this in my slides to events. Now, having all this, we can use that binomial model. So we have 3000 trials. The success probability is 1 over 50,000. We can model by binomial distribution. So a binomial will give the following. So trial is considering if a character is misprinted or not. Success is having a character misprinted, and probability of success is 1 over 50,000. Number of trials is number of characters in a page, so 3000. And under the binomial model, the probability of having exactly k misprinted characters will be this much. And if I will plug the values, n is 3000, k is the number we want to find. Say, what is the probability that we will have 5 misprinted characters in a page? This is the probability that x is equal to 5. We will plug 5 instead of k. Okay, 3000, choose k times p to the k, 1 over 50,000 to k, 1 minus 1 over 50,000 to 3000 minus k. So we can use this formula to calculate the probability of having no misprinted character or 1 misprinted character, etc. And here are the values calculated by R. So the value that, the probability that we will have no misprinted character in a page is 0.94. The probability that we will have exactly 1 misprinted character is this much, 2 this much. So up to x can take any values because we have 3000 characters in a page. X can run from 0 to 3000, and the probability of having 3000 misprinted characters in a page is practically 0. Okay. Now the point is that this calculation is working for a page with 3000 characters. If we will have, say, a page with 3200 characters, then we need to recalculate these things again. Now, I'm giving the Poisson model. Now, in this model, we are considering per page misprints, the average number of misprints in a page. So we will assume that the average number of misprints in a page is 0.06. Why I'm assuming this, where is this coming from? I've calculated that by multiplying p, that p was, if you remember, 1 over 50,000 times n, n is equal to, n was the number of characters, and that was 3000, and lambda is n times p, which is giving that 0.06. So I have calculated by using n times p. Of course, this is one of the ways to calculate that lambda, but usually, in fact, people are not doing this way when modeling with Poisson distribution. People are using statistics. In this case of misprinted characters, we fix some books of that publisher, we calculate the number of pages, we calculate the number of misprints in that pages, say 0 misprint in the first page, 2 misprints in the second page, etc. And we divide the number of misprinted characters to the number of total pages to find the average number of misprints in a page. So this is the general way of calculating that lambda. And in the statistics course, you will cover why this calculation is giving good guess for that lambda. Now, for the Poisson model, we just need to assume that the average number of misprinted characters in a page is given, is fixed. So lambda is 0.06. And we need to assume that misprints are independent, that events of having a character misprinted are independent of each other. Now, under the Poisson model, the probability that we will have exactly k misprints in a page will be calculated by this formula, which is giving e to the minus 0. This is lambda, e to the minus 0.06 times 0.06 to k over k factorial. Now I will give the values for different k's. So the values of x can be 0, 1, 2, 3, etc., 3000, etc. Please note one difference between Poisson and binomial. Binomial was up to 3000, but the values of Poisson random variable can be any non-negative integers. The probabilities are calculated by R by using Poisson probability formula PMF, and you can check that these are rounded numbers, the rounded probabilities coincide for binomial model. But the exact values do not coincide. I will give them soon, but are very close to each other. So these are exact values which are not completely exact, the values that R is giving, because exact values are mathematical, some e to the some number, they are irrational numbers. So the probability that x is equal to 0 by using binomial probability formula is giving this much, and by using Poisson is giving that much. You can see that they coincide for 1, 2, 3, 4, 5 digits. Well, 6 digits in this case. Sorry, let me go back. Sorry. Yeah. Okay, the probability that x will be 1 using binomial model is this much, and for Poisson model is that much. You can see that they are pretty close to each other. For 3, this is 10 to the minus 5. This is machine form of 10 to the minus 5 representation. And starting from some point on, they will be practically zeros, but you can see that binomial model cannot take values in the binomial probability model. X cannot take values larger than the number of characters in a page, 3000. So no values here, but Poisson probability model will give zeros. Say in the Poisson, what is this in fact? This is e to the minus, well, lambda was 0.06, so 0.06 times 0.06 to 3000, very small number, over 3000 factorial. So this is practically 0. Okay. So one note about the difference between distributions. So we have noted that for binomial probabilities, the PMF is defined for k running from 0 to 3000, because if we are doing 3000 trials, 3000 characters in our page, then the number of misprints cannot be larger than that number of trials, number of characters. But for Poisson probabilities, they are defined for any k. And important difference we can see in this example in binomial Poisson approaches of models. For the Poisson model, we forget and do not talk about the number of characters in a page. We just need the average number of misprints. Sorry. Let me give another example of this form. So another example is the following. Assume we own a grocery store and we want to be sure that we will have enough Parmigiano cheese triangles packages daily for our customers. So we can do the following approaches. So we can order a large number of triangle packaged Parmigianos, the cheese pieces, packages, not to have a shortage. So a large number, that will be okay, but this is not working, this is not preferable. We need to spend a lot of money, some of that Parmigianos will not be bought, etc., etc. So another approach is we can order a small number of cheese packages and but this is of course not preferable either. So another wise approach is the following. We can calculate the probability that in a day customers will buy more than, say, K packages. If the probability that customers will buy, say, more than, let me write that, if the probability that X will be 5 is very small, say 0.05, so the X is the number of customers that will buy that Parmigiano cheese. If this is small, then that's okay. We can order 4 cheese pieces and that will be enough for us. We have some small probability that the number will be large, but that's okay. This is our risk and we can take that risk. So this is the approach. So X is the number of customers that will buy that cheese tomorrow. So X is a random variable, and if we will calculate the probability that X is K, X is larger than K for different values of K and choose the minimum of that K satisfying this. So the probability that the number of customers will be larger than K is small. This is just a number. You can take, say, 0.01. So you are choosing your risk level. So we will have some small chance that not all our clients will be satisfied, but that's okay for us. We can take that risk. So in this approach, we need to calculate that probability that X is larger than K. So how we can do this? We can do this in 2 ways. Either we can model X as a binomial distribution, but for binomial distribution, we need to have the number of possible customers tomorrow, n. We can do this, we can model this n by using some statistics. We need to have the probability that a customer will buy a cheese, P. Again, we can do this by using statistics. And then we can model the number of customers that will buy cheeses tomorrow by binomial distribution. And having this distribution, we can calculate this probability. Another method, method number 2, is the following. We can calculate the average daily number of customers that buy the cheese, that lambda. We can do this by statistics, of course. And we can assume that the number of customers follows Poisson distribution with that lambda, and then calculate these probabilities. And this second approach is what people are usually doing. So hope the difference in modeling was clear, and the advantage of Poisson distribution in different cases was clear. Now, another example about Poisson distribution. Assume that the probability of having no misprinted character in a book page is 96% for some publisher. So calculate the probability that we will find exactly 1 misprint in 1 page of that publisher book. Okay, so what we have? Let X be, X is the number of misprinted, let me write misprinted characters per page. This is our unit of a measure we were talking about when giving the definition of our Poisson random variable. So x is a random variable. X is Poisson with some lambda. So we assume that the number of misprints is following that Poisson distribution. We have talked about this. So what is given? We have the following information. The probability that we will have no misprinted character. So no misprinted character is when x is 0. So x was the number of misprinted characters per page. So this is 0.96. So from here we can calculate that lambda. Lambda was unknown. Lambda is not given in the example in the problem, but we can calculate that easily. We know that the probability that x is taking 0 if x is following Poisson distribution is given by e to the minus lambda. Well, I can write times lambda to the 0 over 0 factorial. And this is equal to 0.96. And hence minus lambda is the logarithm of 0.96, and hence lambda is minus logarithm 0.96. Well, because this is a negative number, minus that negative will give positive. So lambda is positive, of course. So we have that lambda. And now the problem is asking, calculate the probability that we'll find exactly one misprint in one page. Please note that if we will use that binomial approach, we need to have the number of characters per page. But here we are not using the number of characters per page because we are using that Poisson distribution. Okay, so problem is asking to calculate the probability that number of misprints will be 1. So probability that x is 1. And we know that this is equal to e to the minus lambda times lambda to 1 over 1 factorial. And this is equal, of course, lambda times e to the minus lambda. We know that e to the minus lambda is 0.96. So this is equal to 0.96 times that lambda, and lambda is minus logarithm 0.96. So we have solved this problem, this part of this problem. Okay, so let's move forward. So next is to calculate the probability that we will find more than 3 misprints in one page of that publisher's book. So we are asked to calculate the probability that number of misprints will be larger than 3. And of course we will use that that complement event probability calculation formula to calculate this. So this is 1 minus probability that x is less or equal than 3. This is equal to 1 minus the sum of probabilities. Let me write that explicitly in the open form. X is equal to k. If x is less or equal than 3 and x is Poisson, x can take only non-negative integer values. So k can be 0. 0 is satisfying this inequality, 1 is satisfying, 2 is satisfying, 3 is satisfying, but 4 is not satisfying star. So we will have only this sum. And now I want to plug the formula for calculating that probabilities. So k is from 0 to 3, and the probability that x is taking the value k under the Poisson model is e to the minus lambda. Well, this was 0.96 times 96 times lambda to the k over k factorial. So k is running from 0 to 3. Lambda is equal to, from here, we have calculated that value of lambda. We can plug it here and calculate this number. So we will have some number here. Okay. Now let's do next problem by using R. Let's solve our next problem by using R. So this problem is asking to generate Poisson random numbers in R, plot in R, and compare PMFs of Poisson random variables with different rates. So take Poisson lambda 1, Poisson lambda 2 with different lambda 1 and lambda 2 and compare the PMFs, and then plot the CDF of some Poisson random variable in R. So let's go to R to solve this problem. So first part was, let me erase this, delete, to generate random numbers from Poisson distribution. So make an experiment with Poisson random variable. So assume that lambda is, L is, say something, say 3.2. So the average number of events per unit of time, say, is 3.2. So Poisson distribution name was Poisson, but because we want to have random numbers from that Poisson distribution, we need to write R Poisson. So R Poisson will give random number from Poisson distribution. So here we need to write how many random numbers, how many trials we want to do. Say one trial with lambda equal to that L. So this will generate a random number from a pseudo-random, in fact, from Poisson 3.2. Yeah, Poisson. Let me run this. So that was 2. Let me run that again. 5. Another experiment, 1. Another experiment, 6. So what is the idea? We have that average number of that events was 3.2. So we are considering one case. In that case, we had 5 events. And in another case, we had just 1 event, 6 events. Say, we are calculating how many cars are passing through my window in an hour. This is the average number, 3.2 cars in average in hour. And one day, during 1 hour, I can have 2 cars. Another hour, I can have 5 cars. Another hour, I can have 1 cars, etc. Say, if I will do that, I can write 10. If I want to do that experiment 10 times, so this command will give possible values. So it is generating random numbers 10 times from Poisson distribution with parameter lambda. So 6 events, 3 events, 2 events, 4 events, 1 event, doing another experiment, 4 events, doing another experiment, 4 events, considering again 2 events, etc. 0. So the average value is 3.2, so that will generate something around that 3.2. The next problem was, let me, before passing to that next experiment, so let me plot the PMF for this distribution. So PMF is given by d Poisson. So what I want to do, I am giving the range of values I am considering. Say k is running from 0 to say 15, and I will calculate the PMF value for each k. Say I will calculate what is the probability of having 0 events under Poisson 3.2 distribution, and then what is the probability of having exactly 1 event in this model, exactly 2 events, etc. So this will give a vector of probabilities, PMF, calculated at the point 0 to 15, and I'm keeping this, say, in y. Okay, and running this. So y is my vector of probabilities. Now I want to plot that, ky, and I want to have in this form with horizontal lines, so type is equal to horizontal. If I will run this, I will have something like this. Okay, so what is showing this? Let me zoom in. Okay, so the probability that I will have 3 events per unit time is large, 0.21, say. The probability that I will have 5 events is 0.11 or 12. The probability that I will have 10 events per unit time is very small, and it is getting smaller and smaller. So I have this kind of shape for the probabilities for the PMF. Okay, now I want to add to this, I want to compare PMFs for different cases, different values of lambda. So let me take another lambda. So lambda is, sorry, this is not correct, 0.5. I have that k, I need to calculate, say, and keep in z d plus the PMF values at k for each value from 0 to 15. Here lambda is equal to L1 in this case. So this is z. I want to add that to my graph. I can add by using points. Okay, if I will add points L1 and Z to this graph, I will have, I want to add a color. Say this is for red color, red. Well, something is not correct. L1, of course, I need to take not L1. L1 is 0.5. I need to take K, sorry. Yeah, I have this kind of thing. So to show everything, let me do the following. So I want to plot in other way. So here I'm writing not H but L. In this case, if I will run that, that will join by a line. Then add here that points, probability points, PMF values, points, yeah, K and Y. So I will have something like this for the first case when lambda is 3.2. Now I want to add to this another graph, but I need to adjust values because for these probabilities the Y values are between 0 and 0.20 something, 21, but for the second one probabilities are much higher. I will adjust that, but first let me take the following. So Z is not Z, I have calculated that Z, but let me plot K versus Z versus K, sorry, and take the color red. If I will run this, let me run this, and that, yeah, I forgot to join them with lines. Type is equal to lines. Okay. So the range of Z is between 0 and 0.6 or something like that. So if I want to have them in the same graph, first I need to keep the previous graph. So I'm running these two. Then I'm adding a parameter new is equal to true. So this is keeping the old graph and doing this. But you can get a wrong, here I have a wrong picture because the ranges, the scales here are not the same. Red is running from 0 to 0.0 to 0.6 and black is from 0 to 0.2. So I need to adjust y values. So I'm adding y lim, the limits of change for y. Say I'm fixing both from 0 to 0.65. I'm copying this. I'm putting it here. Okay, and running everything. So I can select all and run by hitting Ctrl Enter. So I have a correct now picture. And by the way, you can see that it is printing z and y here one over another. You can correct that, but that is not important for me. So I'm skipping that. So what is the idea? Here you can see that for the red one, so if our random variable is Poisson with parameter 0.5, so the average number is 0.5. The probability that we will have 0 events is very large. The probability that we will have 1 event is much smaller, but still high. The probability that we will have 2 events, if the average number is 0.5, is small, and that is getting very fast to 0, tending very fast to 0. Now, for the second case, for the case when lambda is 3.2, the probabilities are concentrated around that 3. The average number is 3.2. So having exactly 3, 0, 1, 2, 3, this is 3, exactly 3 events per unit time or per unit of area is the high. The probability that we will have 2 is high, we will have 4 events is high, and that is getting tending to 0 when k is tending to infinity. And if k is going decreasing to 0, the probabilities are decreasing too. Okay, you can try running this example, drawing PMFs and comparing them for different values of L lambda. Okay, let's go back to our lecture. So yeah, I forgot to draw the CDF graph in R, so let's go back again and do the CDF graph. Say I'm erasing this part, not necessary, this is not necessary for us. CDF. Okay, K is not important for here. L is 3.2. I need to calculate, in this case, I need to calculate the value of CDF at every point. CDF is defined for any real number. So I need to calculate the value of CDF at every point. Of course, this is not important. This is not possible in computer. So I will do that for say t running from say -1 to say 6 by step 0.1. So this will make a vector. The first element of that vector will be -1, then the next one will be -1 plus 0.01, -1 plus 2 times 0.01, etc. So I'm running this. I need to calculate the values of our CDF, and if you remember, the CDF is given by D plus is for PMF of Poisson, R plus is for random number generation, and P plus is for CDF. So I'm calculating the CDF at every point t. This is t. T is a vector of dense points. So calculating the value of CDF of Poisson at t, and parameter lambda is L. And keeping this in a vector y. Now I can plot ty, y versus t. Let's see what is happening here. Yeah, we have this kind of graph. Let me correct this. Let me write type is equal to, because we have, I can, first let me use L. This will give this kind of picture, but because we have stepwise function, piecewise constant function, we can use S. And this is the graph of our CDF of random variable Poisson 3.2 from -1 to 6. And this will continue this way up to 1, tending to 1. Okay. Nice. So let's move forward. One important property of Poisson distribution. The Poisson distribution has the following nice property. Assume that x is counting. X is a random variable that shows the number of occurrence of some event during one unit of measure, say during 1 hour. X is the number of something during 1 hour. If we will model by using Poisson distribution, say x is Poisson random variable with parameter lambda, then the lambda is the hourly average number of that event. So hourly average number of events. Okay, then we can calculate the probability that we will have 0 events. So no event at all in a 1 hour. Or if we will calculate the probability that x is equal to 1, that will give the probability of having exactly 1 event in 1 hour. X is equal to 2, the probability of that is we have exactly 2 events in 1 hour, etc. Now, assume we want to model the number of events, these events, the same events, but in 3 hours. So this model is giving the probabilities for number of events in 1 hour only. So assume we want to model the number of events in 3 hours. So why is the number of events in 3 hours? This is very easy to do in Poisson modeling because since lambda is the hourly average, so lambda is the hourly average number of events, then in 3 hours, the average number of events will be, of course, this will be 3 lambda. If in 1 hour we have 3.2 cars passing by my window, then in 3 hours I will have 3 times 3.2 cars passing through, by my window. So, the average number of events in 3 hours will be 3 times lambda. So why this new number of events in 3 hours can be modeled as a Poisson random variable with parameter 3 times lambda. So this is very important and useful property of Poisson distribution. So let's solve a problem of that type. Let x be the annual number of Atlantic hurricanes. Assume we can model x by a Poisson. Hurricanes are random events, so we can model by Poisson random variable. So x is Poisson with a parameter 5.44. So the first part, what is the annual average number of Atlantic hurricanes? Well, average number is lambda, which is in this case 5.44 because of this. What is the probability of having more than 10 Atlantic hurricanes in a year? So if x is the annual number of Atlantic hurricanes, we want to calculate the probability that we will have more than 10 Atlantic hurricanes in a year, again in a year. So x is annual number. So we want to calculate the probability that x will be larger than 10. So this is 1 minus the probability that x is less or equal to 10, And we know how to calculate this probability. This is a sum of probabilities that x will be 0 or 1 or 2 up to 10. So I will not calculate this. You can do that for sure. And let's continue. The important part is for C and D. So y is the number of Atlantic hurricanes in 5 years. So this was for 1 year. X is the annual number of hurricanes. So y is the number of hurricanes in 5 years. So this is modeled by Poisson 5 times lambda, which is Poisson 5 times 5.44. So these are new parameter for the random variable y, the average number per 5 years, average number of hurricanes per 5 years. And now, what is the probability of having more than 30 hurricanes? So probability of having in 5 years, so we are using that y. The probability that y will be larger than 30. So this is equal to 1 minus the probability that y is less or equal than 30. And this is, just let me write, in this case, of course, because we are talking about random variable y, I will use this as a parameter. So e to the minus 5 lambda is this much, times 5 lambda to k over k factorial, and k is running because I am calculating the probability that y is less or equal than 30, y can be 0, 1, so k is running from 0 up to 30. And we can calculate this by using r. We have the value of lambda, so we have everything to calculate this probability. Okay, let's move forward. Another problem of that type. Assume x is the hourly number of my LinkedIn profile views. Say my profile has 2 views in 10 hours in average. So 2 views in 10 hours in average. But x is hourly number. So this is important, hourly number. And the first part of the problem is asking to write an appropriate probabilistic model for x. So, of course, we will use that LinkedIn profile views are rare events, so I will use Poisson distribution. Now I need to write that parameter. X is hourly number, so I need to calculate the average number of views per hour. Because I have 2 views in 10 hours, then I have 2 over 10 views per hour. Per hour. So the parameter will be 0.2. So this is our model for the number of views, hourly views of my LinkedIn profile. Okay, what is the probability that I will have 1 view in the next hour? So we need to calculate hourly with hourly rate. What is the probability that x is 1? And the probability is e to the minus lambda, e to the minus 0.2 times lambda to the 1 over 1 factorial, so I will have just 0.2. Okay, what is the probability that I will have 3 views in the next 5 hours? So in this case, I will use the following. Let y be the number of views in 5 hours. So the average number of views in 5 hours is the following. So Poisson because for 1 hour I have 0.2, in 5 hours I will have 5 times 0.2. Or if I have 2 views in 10 hours, then in 5 hours I will have 1 view. So the rate is 1. So this is Poisson 1. Poisson 1. Okay, now if I have the distribution, I can calculate easily the probability that I will have 3 views. So I need to calculate the probability that I will have 3 views, but in 5 hours. If I will be asked to calculate what is the probability that I will have 3 views in 1 hour, I will use X instead of Y. But we are asked with 5 hours, so I'm using Y. So that will give e to the this lambda minus lambda, times that lambda 1 to the 3 over 3 factorial. So this will give 1 over, this is 1 over e, this is 6e. So the probability that I will have 3 views in 5 hours is this much. Now, very interesting problem, the continuation of this problem is the following. So intuition will be wrong, can be wrong. Just try to answer without looking at the solution of this problem. So are the following events equiprobable? So the first event is that I will have 1 views in next 1 hour. And the second one is that I will have 3 views in the next 3 hours. Do this A and B, these events have the same probability. The probability I will have 1 view in 1 hour will be equal to I will have 3 views in 3 hours. Let's first solve by using our Poisson distribution. But first pause this video and think about that. Okay. So 1 views in the next 1 hour, we have calculated that, and because X is the hourly number of profile views, page views, then this is e to the 0.2. Well, we have calculated this and obtained this value. And I will calculate this by using R. The next is the probability that I will have 3 views in the next 3 hours. So I cannot use this X anymore. I need to have, say, Z is the number of views per 3 hours. So Z will be, in this case, Z will be a random variable which follows Poisson distribution, but with parameter 3 times that 0.2. The 3 hours, the average number of page views per 3 hours is 3 times 0.2. So this will give Poisson 0.6 Z. And now I'm calculating the probability that 3 views in the next 3 hours. So Z is equal to 3. So what will be this value, the value of this probability? Because we have lambda, in this case, the parameter of Poisson distribution is 0.6, I will have e to the minus 0.6 times 0.6 cubed over 3 factorial. So let's calculate in R to see which one is larger and if they are equal or not. So I'm erasing this. Erasing this too. And going to, well, yeah, I can write it here. So our parameter was, say, L was 0.2. I want to calculate the probability, so d plus, that I will have exactly one view, and this is giving 0.16 and something. This is that probability. Now let me do the following. So our new parameter is 3 times 0.2, and we want to calculate the probability d plus, again, that we will have 3 views, the probability that z will be equal to 3 when that parameter lambda, sometimes I'm writing that parameter name, sometimes I'm not writing. Important thing is to write the value of that parameter. The value is 3 times L, or 0.6. Let me just write 0.6. So this is that probability. And you can see that this probability, the probability of having 3 views in 3 hours, is almost 10 times less than the first probability, this probability. Is this intuitive or not? Can you explain why the probability of having this is not equal to the probability of having that? Let me try to explain why is that. So the idea is the following. Say this is our timeline: 1 hour, 2 hours, 3 hours. Okay, so the probability that z is equal to 3, so we will have exactly 3 views here during these 3 hours, is not the same as having 1 event here, 1 event here, 1 event here, 1 view in the first hour, then 1 view in the second hour, 1 view in the third hour. Z is equal to 3 consists of the following events. So we can have either 3 views in the first hour. So 3 events in the first hour, 3 views in the first hour is the following. So x is equal to probability that x is equal to 3. So 3 events per first hour. Then no event in the second hour. So again, x is per hour number of views. So, and then again, no view here. So I can in fact square this. I'm writing this because of independence of number of events here and there for the first hour, second hour, third hour. Plus, but this is not all. I can have the following situations: 2 views here, 1 view here, and 0 views here. In that case, I will have 3 views during that 3 hours. So this is the following. So probability that 2 views here, x is equal to 2, then 1 view during the next hour, then 0 view for the next hour. But in fact, I can have that in, this is not exactly correct because I'm not considering the following cases. Well, this is not complete because I have considered the case when we have 3 events here, 0 here, 0 here, but we can have 0 events here, 3 here, and 0 here. So I need to multiply by 3 because we can have this kind of pattern: 3 views for the first hour, 0 views for the second hour, then 0 views for the third hour, or 0, 3, 0, or 0, 0, 3. And the probability of each of these pattern is given by this product. So 3 times that plus how many times I will have this kind of shape. So I can have 2, 1, 0, so 2, 2, 1, 0, or I can have one view in the first hour, then 2 in the second, then 0, etc. So if I will calculate all these kind of things with 2, 1, 0, I will have 6. I have 6 cases here. And another possibility is when I will have just one view for the first hour, one view here, one view here, and that will give 1, 1, 1. The pattern will be 1, 1, 1. The number of views in the first hour, second hour, third hour. So this is the only case, so I will have this kind of thing. X is equal to 1, then the same probability that x is equal to 1, the same probability x is equal to 1. Because of independence, I will have this cube. And you can calculate that this is giving exactly what we have calculated before by using R. So this is the explanation. So having 3 views in 3 hours consists of different cases. That's why having one view in 1 hour is not the same as having 3 views in 3 hours. Okay. Sorry. Now assume that X is the number of pizza orders at Pandok Yerevan between 1 p.m. and 3 p.m. Hope this is a rare event. This is a rare event, so we can model that by a Poisson distribution. So X will be a number of pieces. So X is a Poisson random variable with rate 2. So during these 2 hours, people in average are ordering 2 pizzas. So find the distribution of the number of pizza orders at Pandok Yerevan between 1 p.m. and 3 p.m. at the same time for days when there was at least one order. So what this means? So in fact, if X is the number of pizzas orders during this time period, X can be as well 0. So the average number is 2, but sometimes we can have 0 orders, sometimes we can have 1, sometimes we can have 10, say, orders, etc. Very rare 10 events, 10 orders, etc. But the problem is asking calculate the distribution, probability distribution of number of pizzas. So we will have PMF for that days when there was at least one order. So we have some information about the number of orders, about X. So what is the problem asking? What the problem is asking is the following. So we need to find what is the probability that X is taking the value K. We need to distribution of number of pizzas. X is K, given that we have at least one order. So the problem is asking to find these conditional probabilities for any possible K. So we remember that, of course, the probability that X will be 0 given that X is larger or equal than 1 will be 0. So K is starting from 1. So K is starting from 1. K can be any natural number. By the definition of this conditional probability, we will have the following. X is equal to K and X is larger or equal than 1 over the probability that X is larger or equal than 1. So because K is larger or equal than 1, this event will be, so X is equal to say 3 and X is larger or equal than 1 is X is equal to 3. So this is the same as to write probability that X is equal to K over the probability that X is larger or equal than 1. So now let's calculate. We have that x is, so let me write somewhere here. So x, what we know about x. So x is Poisson with parameter 2. Now the probability that x will be k is e to the minus 2 times 2 to k over k factorial. And this divided by the probability that x is larger or equal than 1. This is by passing to complement the 1 minus the probability that x is less than 1, and the only possibility is when x is 0. And this will give e to the minus 2 times 2 to the k over k factorial divided by 1 minus the probability that x is equal to 0 will be e to the minus 2. So this is the distribution. This is the PMF for this conditional random variable. And k is running from 1. The possible values of this can be 1, 2, 3, etc. Okay. So next, with next video, I will give some examples of data fitting using the Poisson distribution. I will use R to model to show. I will use some real data for that.